Inside this chip, there are switches. Each one has exactly 2 states. Current flows or it doesn't. 5 volts or 0 volts. Today's computers are electronic, not mechanical. Digital, not analog. Binary, not decimal. Every signal in there is one of 2 things. 1 or 0. You already know this part. Computers work in ones and zeros. And to do arithmetic, you'd think it translates that code back into real numbers. Here's what bothers me, and it should bother you. Nothing in that chip translates. There's no dictionary in there. No lookup table between your wires and arithmetic. Which leaves us a question. If a wire is only on or off, how does a wire hold the number 231? Start with the simplest way you could write a number, 1 stroke per unit. It's useless, write 2000 and you'll need a wall. Place value fixes that. The space you need grows with the logarithm. Take 6083. You read it without thinking. But watch. 6 thousands plus 0 hundreds plus 8 tens plus 3. 6 times 10 cubed plus 0 times 10 squared plus 8 tens plus 3. So you've got 2 moving parts. A digit and a place value. The digit tells how many. The place value multiplies by 10 leftward. The digits you get run from 0 to 9. That's 10 symbols. 9 is the end of the road. Add 1, open the next place. Now look at the rule with me. Digit times place value, summed. Where does 10 appear as a requirement? Nowhere. So what if we put something else there? In the 1800s, a British mathematician, George Boole, did something apparently pointless. He wrote an algebra. Not for numbers, for quantities that were true or false. 2 values. That's all his variables were allowed to be. Think how strange that was. Calculating machines were decimal. 10 positions on a wheel. Brass teeth springs. Nothing there suggests 2. Boole wasn't designing hardware. He asked what your reasoning looks like as algebra. Nearly a century later, someone builds a circuit out of switches. And that circuit obeys Boole's algebra. Physically, not as an analogy. Boole had the algebra. He had no idea it would ever be wired. Back to our rule. Same structure, but each place is larger by 2. Only 2 digits exist now. The unit's place holds 0 or 1. So how do you write 2? It already needs the next place, 1, 0. Let's read 1. Take 1, 1, 1, 0, 0, 1 in base 2. The places from the right are 1, 2, 4, 8, 16, 32. So that's 32 plus 16 plus 8 plus 1. 57. Now the other direction. I hand you 45 and ask for binary. How? Divide by 2, whole number division. Write the remainder. Repeat until 0. 45 over 2 is 22, remainder 1. 22 over 2 is 11, remainder 0. 11 over 2 is 5, remainder 1. 5 over 2 is 2, remainder 1. 2 over 2 is 1, remainder 0. 1 over 2 is 0, remainder 1. Read your remainders bottom to top. 101101. Check it yourself. 32 plus 8 plus 4 plus 1. 45 exactly. So we can write any number as ones and zeros. Can we add them? Here's the engineering side. Suppose you wanted decimal on the wire. You'd need 10 voltage levels you could tell apart, surviving heat and interference. Now try 2 levels. Roughly 5 volts or roughly 0. Those are absurdly far apart. You'd have to try to confuse them. That's your argument for base 2. The smallest base that counts. An adder is built from components with 1 or 2 inputs, 1 output. Those components are gates. An AND gate is a few CMOS transistors. The hardware wants 2 states. But addition needs carrying, and a switch can't. Okay. Carrying is the same in every place value system. You know it already. When the sum in one place reaches the base, you carry. In base 10, the base is 10. Here it's 2. The only change. Add 1 0, 1 1 0, 1 1 to 1 1 0, 1 1 1. First column. 1 plus 1 is 2, in base 2, 1 0. Carry 1. Next column. 1 plus 1 plus your carry is 3. Write 1, carry 1. Keep going the same way. Nothing new, just 5 more times. Your answer, 100,100,10. Let's check in decimal. Those two numbers were 91 and 55. 91 plus 55 is 146. Your answer, 128 plus 16 plus 2. 146. It works for the boring reason, same arithmetic. Now the payoff. That carrying addition is what the full adder performs. 3 inputs, your 2 digits and the carry in. 2 outputs, sum and carry out. In base 2, how many things can one column plus a carry be? 4 cases. That's the whole problem, and it fits in a few gates. Nothing was translated. The machine was in a real number system throughout. 6 binary digits for 45. Unreadable, but that's our problem, not the machine's. So we cheat. Take the binary digits and group them in 4s. 4 places hold 16 values. So each group becomes 1 hexadecimal digit. But we've only got 10 symbols and need 16. So A through F join 0 through 9. Take 1101, 1010, 0110. That first group, 1101, is 13. And 13 is D. The next is 10, A. The last 6 stays 6. So D is 6. Here's the thing, did a single bit change? No. Only the notation moved. Hexadecimal isn't a number system the computer knows. It's never heard of it. It's a convenience for whoever's reading the screen. That's you. Nothing in that chip translated anything. It counts in the smallest base that works and carries the way you were taught at 7.